Cython, who has it installed? Oh, hands high. Be proud. All right. On Macs, it's pretty, so on Macs, especially if you have Homebrew and have the compiler already installed, then you should just be able to do pip install Cython. It should work. It should use whatever compiler is there. It needs a C compiler. Getting the right version of a compiler on Windows can be tricky. We'll use Visual Studio, but it needs to be the Visual Studio that your Python was built with, and so this can get a little hairy. So please, especially people who plan to do work on their Windows machine, doing native work, try to install Cython sooner rather than later. A good test case would be the stuff that I'm going to do today. There are instructions at docs.cython.org, post on Piazza, come to office hours, something like that. We're going to be using Cython for the next homework. There are going to be more demos that involve Cython, and so if you want to be able to follow along, you'll need to have it installed. So please try to do that soon, just for your own sanity. All right. Today, I'm going to talk more about multiprocessing and communication costs. We talked about last lecture. Difference between multi-threading and multiprocessing is really that you have separate OS processes, but as we talked about, those are under the hood. Those are basically the same. Like a different process is just a separate single-threaded process is not that different from just two threads in the same process space. They use the same code. The threads share memory. The separate processes basically share nothing by default. They're not really different that much in costs, except under Windows where there's a bias towards threads being used. The real difference comes down into the paradigm that you use for communication. Multiprocessing uses message passing. You have independent processes. They talk back and forth with messages. Threads tend to use just shared memory and locks. They just write values, read values. Something else will read it. They use locks to make sure that they don't overwrite each other's work or there's not contention. So we're going to look at this. There's a cost associated with message passing, though. Okay. Like I said, multiprocessing shares nothing by default. They communicate with message passing, so there's an overhead to that message passing called serialization or marshalling is another term for it. We don't share a memory space. I need to talk to you. I can't just pass a pointer to you and say, look at this data. I have to tell you what's in the data and pass that to you. Then you have to reconstruct it. So objects, arrays, strings, dictionaries, lists, whatever you're passing back and forth, need to be converted to byte strings, some sort of shared format. In Python, that's called pickle. That's called pickle, if you see that word, and just spelled like pickle the word. It's the serialization format for Python data. So you can take most Python objects, you can pickle them, it turns into a string, you can write that string to a file, you can read it back into a different Python, you get the same object back. When you're talking about inter-process communication, the two processes, one of them converts the object it wants to communicate. I want to hand you an array. It converts that array to a string of bytes. And we don't need to know the details of the format. It converts it to a string of bytes, writes it via the operating system to the other process. That mostly just stays in memory. It's just a memory buffer that looks like a file in general. So there's not the time to go to disk, but there's still the cost of writing. And then it's read in the other process and decoded and turned back into an object of a Python object. Okay? Is it clear what's going on here? I can't just hand you something, right? I can't just hand you an array out of my process space. I have to give you a description of it.
So you only use serialization when you have shared processes, correct?
When you have, basically anytime you have inter-process communication, separate process communication.
Separate process.
Yeah, when you have separate process, you don't need to with threading.
Right.
In threading, I can just give you the Python object directly, basically a pointer. I can just say, look at this memory, and you can look at the memory and you see the array there. But if you can't look at the memory because you're in a different process, right? They're in separate memory spaces. I have to tell you what's in the memory. I have to take whatever's there, convert it to a transportable format, send it to you, and then you have to decode back into your own copy of the array. It's different. It's a copy. It's a different piece. Whereas if we're threaded, we're using the same memory. All right. And we
avoid doing this stuff?
Yes. I'll show it. Yeah, exactly. That's what the rest of this is about. Well, first we want to understand how costly is it, right? So this is experiments with how costly is it? How much does it affect our computation? It's costly, but you trade it off with complexity, right? Message passing is very clean and very easy. You don't have to worry about, there are a lot of things you don't have to worry about that you do have to worry about threads, like shared memory and locks and things like this. That goes away with message passing. The problem is you pay for it in performance. All right, experiment time, especially for people who've installed Python and cloned this repository. It's just a Mandelbrot computer. There are several versions in there, serial, multi-threaded, blah, blah, blah. Why Mandelbrot? Why, who cares, right? It's nice because it has a lot of computational density, right? There's a lot of work done at each pixel. And pretty pictures are good feedback. If you screw up your algorithm, it produces the wrong picture, you can tell. So I prefer experiments that, I like to do graphics experiments, image processing experiments, and things like this, where you get immediate feedback that's, yes, it's right, no, it's wrong. And you can usually tell except for sort of little off by one errors, which you usually don't care about. So if you've cloned this and want to follow along, this is the Mandelbrot function, all right? It's slightly optimized versus the, just iterate over a single value, okay? So this version, I'm taking arrays in, and I'm going to write arrays out. And this will be important later when we get to the optimized version. So the incords are the inputs to the Mandelbrot function. Who is not familiar with the Mandelbrot function now? I mean, you should have done it in homework 1, right? It's just a little fractal. It's got a very simple computation of iterative, right? Take a complex value and do this iteration over and over. And if it flies off into space, it's outside the set. So that's what I'm taking in. Incords is just the incoming complex values that I want to compute for. It's an array because I want to do it over pieces for a large number at a time. I don't want to pass a single value in, compute for that single value, and then return the result for that because it's not as efficient as this. So we're just going to jump straight to working on blocks or full arrays of coordinates and returning their counts, all right? So the function is, the Mandelbrot function takes complex numbers to an iteration count. When did it escape from a certain circle, all right? Right here. So these are the arrays. I'm going to take in 2 arrays of the same size, in coords and out counts for each, and then I'm just going to loop. You can see looping over the 2 shape values. I pull out the complex number, I iterate the loop, and then spin here, computing. I either hit the maximum, right, max iterations, or I break out because it's gotten too far away. Okay, once it gets above 4, once the squared magnitude gets above 4, it's guaranteed to fly to infinity. And then I just write out in the same location, this ij location, the iteration. So I'm going to do that for this whole block, whatever's passed in. I'm going to pass in an array, 2 arrays, read out values from one array, compute the iteration count, and write those out to the output array. Right? Is this clear? This is Python. So this is the slow version. All right? No, you're right. Yeah. So there's where this is like what I said, lots of work per memory read. So we read basically 1 coordinate and we spin here for up to 500 iterations. Or actually, most of the examples here, I'm going to run it for 1,000 or so to increase the time. This is Python, all right? I wanted to show the Python first because really, almost everything is the same. And I want to emphasize that. Basically, everything in this block is identical. So the Python is the, if I give it types, it'll turn it into pure C code. So I say, okay, I want this to be a C and Python function. That's the CPDef. I give types for my arrays, including the fact that they're 2D arrays. Complex values coming in, integer counts going out, and then there's an integer. The maximum number of iterations is also an integer. And then I also give some types for the internal variables that I'm going to use. And then with that, that's enough that I can assert this with no GIL. We talked about the GIL. GIL basically means the GIL is used for interpreted Python code or any calls into the Python library. This says, I don't need the GIL. I have no interpreted code below this point. We'll use it a lot in Python code when we start writing our own, or you'll see it a lot. We're going to hand you a lot of Python code, but when you need to write your own, you use that also to assert everything below this. I've given you enough type information. You should be able to write pure C code. And so it's useful for both those purposes. One, it drops the GIL. Two, nothing in here can be Python. It cannot go into the Python interpreter for any reason. And so by putting that in there, if this compiles in Python, I know that I've done enough typing at the top, given it enough type information that this is pure C. Is that clear? Are those two parts clear? The types and the no GIL.
You have to write the bottom. Sorry, you have to write the bottom part, like, with keeping in mind that because now there's no GIL, you have to write code in such a way that won't cause it to break or something like that, or is it just going to take care of itself?
It won't take care of itself. No, you do. And you have to be aware. So so for example, if I put in a call to another Python function, like print, if I put a print statement in here, when I give this to Python, it's going to say, you can't call Python functions when you don't have the GIL. If I reference some global variable, which I could also do. So Python is a superset of Python, I think just entirely now. So I could put arbitrary Python code in here, right? I could reference global variables. I could even pass in, something without a type, another argument. But if I reference it here, it says, well, it's a Python object. I need to go into the Python interpreter to find out what's there. And it'll crash. I mean, in the compilation, it'll blow up. So by putting that in and then making sure it still compiles, I know that I have done everything.
Is there like a list of do's and don'ts then when you're writing certain things that are obvious? Or?
It often ends up, so not do's and don'ts necessarily.
I mean, like if I write with no GIL, like make sure you don't say. Like,
Oh, it'll tell you.
You don't do like a certain. Something.
It'll tell you. It'll just say no. Like it's two stages. So Python first turns everything into C and checks, the assertions that you've made, and then compiles that C into a module that is loaded into the Python interpreter. So if it doesn't get past the first phase, then you know.
Tell you where exactly.
Oh yeah, this is right here. Once you are in sort of Python mode, think of it more as C. Then you start thinking about memory access patterns and stuff like that, and order of operations, stuff like that. But in general, you don't have to worry about it. You can also do things like, okay, I'm trying to debug my no GIL section. I can add a with GIL and print something, right? And then I can basically, I could put down here, and we'll show this probably when we do more Python, with GIL, and do another block and say print and reference global variables, get back into Python for debugging purposes, which is useful to remember. So, sorry, what? So if do you have the repository up? So it actually has. So you see up there in the types. Let me highlight it. You see in the arguments, I've got this MP complex 64T. So you can import NumPy just like you could in Python, but you can also do this C import. So if you look at the actual code in that repository, at the top it's got C import NumPy as MP, and what that says is give me all the C side of NumPy, which is things like MP complex _T. So usually in NumPy, when you reference a type, you don't put the _T. That's the C side of NumPy. So you can still basically import all the modules that you usually would want to. Only some of them are going to be fast, and if you call into a module that's not compiled, right? So, or that Python doesn't know how to dig into the insides, then you have to go through Python, and so you can't do it in this sort of no GIL section. You basically have to have the GIL to go into those modules, all right? But several of them are, and NumPy is really well supported. So arrays and anything that has the buffer type, you can do things like this. And so I can pass NumPy arrays to this, and it immediately just unboxes the NumPy array, right? Because the NumPy array is a block of data and some meta information. It just goes to that block of information and treats it like a C array. Okay? No, it would, well, it would be slightly different. One, the code's going to be exactly the same that's produced by Python. The one thing that will be different is I'll still hold the GIL when I go in there. That won't matter here because we're doing multiprocessing and we don't care about the GIL. I'm gonna have some number of workers, but each of them has their own GIL. When we get to threading, I wanna show this now, so you're used to the idea. When we get to threading, if we don't do that, then we're still in GIL land, right? Where one piece of code is in this block at a time. I like the no GIL, I use it just as an assertion of this is all pure C, right? Because if it doesn't have the GIL, it can't do any Python calls. So it's useful just to make sure that I've done all of my types. I haven't missed a variable. If I take out the declaration for iter, then this won't work because it says iter. Well, that's just a Python object because you haven't defined it. And it says, well, I can't do that. You're in pure C mode. Okay. Okay. All right, so this is now a fast mountable function. It's very computationally dense. It's gonna sit in that tight loop. When we call it, it's basically pure C. And it's just gonna sit there and do it as fast as if I'd written it in C. All right, so let's see how it does. There's a bunch of extra sort of stuff, and so let's look at, so here's my Cython code. Cython has the PYX extension. There's extra stuff in here, just so that you're not surprised by it. Like I said, there's those C imports at the top that give me access to the C side of things. I have this magnitude squared function. You can look at the declaration. It takes in a complex. It spits out a float. It looks just like, almost like if you were to take a C function and translate it into Cython, or into Python, yeah, where I've added types in. Also got the no GIL thing to say this can be called without the GIL. Everything else is the same. There's the bounds check and wraparound. That just turns off some extra array checks. NumPy, it basically turns off safety checks and doesn't allow me to index with negative values. All right, but the rest is the same, okay? And here's the, actually I have slides for this. Oh, no, maybe I don't. Here's the code that calls it. I've got a common module that sets up a bunch of things. I get the coordinates, I just create those. I've got an interesting area of the set to look at. I've got a timer, and then I just call right there, the mountable, coordinates, counts, and iterations. Maximum number of iterations, 1,000, okay? And then print out some information and display a picture. So, run, goes for 5 seconds. Somewhere I have a picture. Oh no, where's my picture? There it is, all right. Voila. So 4K by 4K image, about 5 seconds. It worked, right? This is why I like to do this. It's like, okay, I know that my algorithm is roughly correct, all right? Okay, let's look at the times. So, as we learned in homework 1, we can just sum up the counts and get an idea of how much work we did, right? How many iterations did we do? So that's that bottom number. Total of about 1,000 million complex operations. That's FMA is, shouldn't be F, it should be just multiply add. It's basically how many iterations is a multiply and an add of a complex number. We'll talk about FMA as a floating point multiply add. Is a standard instruction on a lot of machines because it's very useful for things like dot products. Anyway, then we see we get about 200 million operations per second in single processor mode. Right? Okay, so that's our baseline. That's one core of a 4-core machine. Takes about 5 seconds. About 200 million loops per second. Which is pretty good. It's reasonable. It's like a 1.7 gigahertz machine, 1.2, 1.3. All right, but it's actually, I've got more power here. I mean, it's not a big machine, but it's a 2-core machine. Each core can interleave 2 threads. This is what's known as hyperthreading. Basically, it has very fast switching between 2 threads on each core. So it keeps basically 2 threads ready to run at any time. So if one of them stalls on a memory access, the other one just starts up right away. That's called hyperthreading. You may have heard about it. That's all it means. And it's almost always, I don't think they do anything more than 2 threads, right? So it's 2 threads per core, also known as hardware threads. So I have 4 threads total, basically, that I can take advantage of. And it can be even small stalls, like, I'm waiting for the multiply unit to come back, which has a latency of like 3 instructions, right?
Threading and hyper-threading like the same thing?
Depends on the context of threading, right? Threading above, we're talking about, well, we have threads within a process space. And we could have, I can start up any number of threads in a single process. But if you're talking about hardware, usually talking about hardware threads or hyper-threading, things like this, it's basically how much context does the CPU hold? Because each thread has a context, right? It has its registers, it has its program counter, things like this. The very low level, what am I working on right now at the very bottom hardware level? So when I ask, when I ask the computer, like, how many processors do you have, how many CPUs or whatever, it's going to come back with something like 1 CPU with 4, and it says like 4 cores. It doesn't actually have 4 cores. It has 2 cores, each of which can run 2 threads. It's not critical but it can, when you're thinking about hyper-threading, if you've got 2 threads in one process and they're on the same core, then then they're sharing the L2 cache, and they're sharing the L1 cache. If they're on different cores, then they're not sharing that, and is that good or bad? Depends on what you're doing.
Then how is that separate from regular, what we were talking about, I guess, more of the software side of threading?
So the software side, you're going to have some number of threads, and including the entire OS, right? And the operating system is responsible for saying which threads are running when, and it basically has. That's where the scheduler comes in. The operating system scheduler has. I've got 100 tasks.
Is that just like an applications that are running, or?
Yeah, applications. It's whatever I'm doing. It's basically everything, right? When you type PS or you look at the task manager, you have a bunch of things going. And the operating system is responsible for saying, I have 4 hardware threads. I'm going to choose which one is going at any one time. And one of them might be the operating system sometimes, right?
So you could have potentially 100 threads open for whatever, for some reason.
Oh, yeah.
So
And
okay, we're talking about next year.
That's-
We're talking
yeah.
for the next.
no, this is like the low level, like what can it actually do? So let's just call this machine a 4. Let's say that this machine can do about 4 processes at once. So we were getting about 200 on single threads on a single processor. We'd hope to get about 800, right? That's our goal for perfect speed up on this machine. All right, that's really the important part here. I mean, all the rest of it's all important, but what we're looking at here is we have 4 times as much processing power as we were using in that last example. Hopefully, we can use it all, right? We've got an embarrassing parallel problem, right? Each pixel, each count at any one location is totally independent from all the pixels around it. So it should be embarrassingly parallel. All right. So multiprocessor version 1. We're just going to take the image. We're going to break it up into blocks, 10 blocks by 10 blocks. I think I'm doing 4K by 4K images, so that comes out to 400 pixels on a side. And then I'll show this. I've got a generator that takes an array in common.py and dices it up. It just takes a NumPy array and returns it in pieces. Those pieces are sent to the workers. And then in the multiprocessing one, it's going to send it out to 4 workers, compute on those blocks, read back the results, and then write that into an output. Okay? So it's going to just look like this. So you don't need to understand necessarily what by blocks does. It just cuts it up. So with the in blocks, I've got the function, and so this is the one that dices it up. I've got my, it's the same thing. I've got my in coordinates, I've got my out counts that I want to compute. So first thing is I dice up the coordinates into 10 by 10 blocks, right? Is it clear where I'm going with this, what I'm saying when I say dice it up? Okay. And then I'm going to I'm going to create a pool. I've already created a pool of 4 processors, and I'm just going to map the function. I'm use the basic map functionality, which takes calls a function on each of those blocks, and then I'm going to get a list of results, and I'm going to write those results right here. I've got my result, and I dice up the output in the same fashion, and then write out to each of those output blocks. That's what dest is. the result. Okay, clear how this is being built? It's being cut apart. The input and the out counts are being cut apart. 100 blocks. That's 10 in each dimension. So.
Is it random 10 or is it
10 in order. 10 in order. But the map is going to run. Map doesn't necessarily run in order. It gives me my result back in order, but it doesn't run in order. Okay. Okay, question, where is the serialization happening here? What is being serialized? What? Yeah, so right here. There's serialization here when I send those blocks out, right? I've got blocks of coordinates of complex values in the array. I send those out. And then I receive them after the map finishes, right? The worker receives a block. The driver, this program, takes the array block, serializes it, right? It's got a 400 by 400 set of coordinates, or of complex values, serializes it. So it turns it into a byte string, converts it to, here's an array, it has these values in it. Communicates that to the worker here. The worker reads that, rebuilds that array in a new memory space, new copy. Calls the Mandelbrot function, computes, gets a result, an array of counts, serializes that, passes it back to the driver, where it comes back here and is rebuilt as an array, all right? New copy. And then I have to copy those into my actual destination. So dest right here is the out counts, okay? Is that clear? It's not the cleanest way to do it because of this. Especially because of this serialization where I make a new copy and I have to put it into place. Right? Let's see. Good question. In a second, okay? Here's the rat Mandelbrot, just so that we can, for completeness. Because Mandelbrot, the low-level function, we were passing in two arrays, an input array and an output array. I need to create a temporary output array. Because the workers get this block. They don't have the output array, the out counts array back on the driver. Needs to create a place to put its result. That's what temp counts is. So it uses that as the second argument. That's the output. And then returns that. And that's what gets serialized, this new subarray. So that's going to be much smaller. The full output counts is 4K by 4K. Since we're dicing it into 100, this one is only 400 by 400. Okay. Let's see. So, isn't that a lot of overhead? Four times as many workers, right? So, in Unicorn, Happy Land, I have 800 time. I get 800 million operations per second. I don't. I get like 488, right? Did I get the same? I get the same answer, right? It all works because I'm not doing this live. But I'm nowhere close to optimal, right? In fact, I'm just barely over. I have four processes. I'm basically getting like 50% efficiency. Okay. The total amount of work I did is the same. That's good to check. But I didn't do it very much faster. Okay. And why? Because I'm passing around a bunch of extra stuff. Right. So, I'm sad. So, serialization for problems like this, where I'm passing around all the data I'm going to process, means that my serialization cost is the same order. It grows as big as my problem, right? That's horrible. That's a problem for both Amdahl's law and Gustafsson-Barsis, right? Gustafsson-Barsis allowed us to say, well, I have more computers. I'm going to solve a bigger problem. I'm going to get better efficiency that way. Yeah, sure, as long as your communication costs don't go up. That's sort of the downside. If your communication costs also grow, then you don't get really any benefit. All right, it's a problem. How do we avoid this? Ideas? Yep. Between Python and C? It's happening between Python and Python, actually. I mean, it drops down into C. So it's, before the C code can be called, I need an array. And NumPy arrays are very efficient. That's why we're going to use it a lot. They're basically C arrays. They're the same. So in the serial version, I have a C array, and I call into the C code, and it just evaluates it and writes out another C array, and then up above, that looks like that's a, Python can use that through the NumPy array. Yeah, the C in the Python is just which language are we running in the interpreter, or are we running in a module that's in the same process space? So when I load in that Python module, when I compile that Python module and import it, becomes part of the Python interpreter. The Python interpreter is written in C. Now I've got another piece of C code that is also working there. The serialization here is working between processes, because one of them has a bunch of data it wants to work on, and the worker needs to do the work. I need to get that data to the worker, and then get the result back. And in this case, this slow version, we're just passing all of the data. Okay.
Is that serialization a big problem for Spark?
It certainly can be. It's not so. If you're talking about communication between machines, serialization is on the order of the cost of setting up a connection and transferring data, right? Because machines are very far away. You have to go to the network. So the cost of turning data into a serial format and passing it across, not that much worse. I think they also have a very fast serializer. They have a special one called Kathmandu or something, I forget. But they try to address that. But there's also just if you're doing shuffles, you're sending stuff right.
Since we're only 2 cores, why don't we expect the speed up to be closer to twice as fast?
So the cores here, there are 2 cores, but each of them actually has what? So when I do a multiply has a latency, and it's long. It's like 3 to 5 cycles or something. So in the meantime, if I just had a core running, right, and I did a multiply, it would just, and this is the bad old days, it would just stall and wait. 3 cycles later, I would go on. Modern architecture has all kinds of like crazy out of order and speculative stuff. And one of the things they've added is you basically have in your CPU, you've got some logic. It's usually drawn. I can't draw it. You've got a bunch of state and logic and compute and registers for and L1 and whatever. What they do is, this is the state for one thread, and they have all the state for another thread, all the registers. The L1 cache is still shared between these two, but it's basically everything you need to be running a program. They have 2 copies of it right here. All of this is just 1 copy. All the logic, all the arithmetic unit and things like that, there's still 1. But if process 1 launches a multiply and has to wait, the core immediately schedules something from process 2. Right. And so process 2 can now start taking up the hardware. So this is hyper-threading. It's basically there's enough compute in the core to be doing 2 things at once, as long as you can keep them fed. And since a lot of things require a delay of 1 or 2 cycles, you just have 2 threads there, and it's like, okay, I'll do something for you and something for you. One of them will be using multiply, one of them will be using the add unit or something else. And so that's when you see, that's hyper-threading or hardware threads is what that means. So we actually, the computer can actually do close to 4 times as much work as any single threaded thing because of this. I mean, not always. I mean, if there's something that they both want to use a lot, like multiply logic, then it won't work. It won't help. But in general, you've got a bunch of things going on at the same time, and they can be interleaved. So that's all. It's like I have 4 cores. I have something slightly less than 4 cores, but in general, it gets actually pretty close. All right. Before we go on, how can we avoid serialization? That's a good answer. We're going to do that later lectures. Why does threading, but to get to this, what does threading avoid? Why don't we need serialization for threading? I don't even know who said that, so I'm just pointing at all of you. You! Why don't we need serialization for threading? Right, shared memory. Guess what? We can have shared memory in multiprocessing. And we're going to show that as a step towards actual threading. You can use shared through memory in multiprocessing. The operating systems support it. Multiprocessing module gives it to you as value, which is just a Python value that's shared or array. But then you need locks, right? Then you're like in the worst of both worlds. You're multiprocessing with all the overhead of separate processes, but you have to do locks and stuff like this. But in this case, we don't have any locks. We don't have any contention, right?
I'm still a little confused where the serialization came in, because it seems like the Mandelbrot, like you said, like you could just chop it up into 100,000 different arrays and completely calculate, like reduce it between those arrays, execute the function, and then map it at the end.
Right,
So
right.
why is
But I'd have to compute back. So even if I were handing off a more condensed form of the serialization to the workers, they produce a block of data, right? Some subtask. And I have to get the results of that subtask back to the main process, right? And to do that, I can't just hand it memory. I could save it to a file and ask the other process to read it, but that's the same as serialization, right? In a sense, I've taken it and I've put it in another format that can be read by another process and reconstructed. So the serialization is, I've got a result or a task. I've got some block of data that represents. I need to communicate it to someone else. Okay.
So is that bringing it all together after the computation's been done, or is that?
Right. I mean, in this case, I could have come up with a much more condensed, I'm doing blocks of a known value. So I could have come up with a much more condensed way of giving it to the workers, but I would still have to read the whole block back. And so I'd still pay half the serialization cost in any way.
In this case, are the workers the cores or the threads?
Yeah. Well, in this case, it's the pool. When I say pool 4, it gives me four processes, each of them single-threaded, that are going to do the work. Okay. Is that cleared up? It's basically, so think of the the bookstore example, where they were counting coins, right? Imagine instead of counting coins, they were, taking a picture of the coins, right? And now they want to combine those in a book of all the coins I paid with my books with, right? I'm going to take a picture, and I've got it on my phone. I need to get it to someone else. How do I do that? Do I have to print it out and hand it to someone? Do I have to send it in email? It has to be converted to another form and handed to you in a way that you then have it. And so that's what serialization is.
Okay.
All right? It's basically the communication of data between the processes in a common format.
Okay.
All right? Don't know how much. We'll do the next part. There are a couple more parts after that, but we'll get to those later. All right, so let's use shared memory. All right, this is more about, right, if we're going to use shared memory, you might as well do in threading. This is more to talk about the costs of serialization. So to get at that. So what we're going to do is we're going to use shared memory for the two arrays, right, the version 2, which is in the multi-blocks. We use shared memory for the input and output arrays because no one is writing to the same part of the output arrays. It's diced up into independent parts. We're going to send slice coordinates to the workers. We'll talk about that in a sec. The workers will then read and write from these shared arrays, just like regular memory. There's no overlapping computation, so we don't need any locks for this problem. It's more just about let's reduce the serialization and see how much it was costing. Okay? Slices. You're going to have to learn slices. It's not that hard. If you've done NumPy, you've probably already done this. So you have a NumPy array of some size, 100 by 100, and you just want the upper left corner. If you want just the upper left corner, you do something like this, right? People have seen this notation. This may be new if you haven't done NumPy before. If you haven't, you should look at like a NumPy tutorial because we'll be dealing with images and things like that. This is basically give me the top 10 by 10 corner of A. An important thing to remember is it's the same memory as A, okay? If I take that and I modify a value, if I assign that to a variable B and then modify some value in it, it modifies A. It's a piece of the original array, all right? Sometimes we want to talk about slices as objects themselves. And this is the notation for that. It's a built-in function in Python. Basically, it's a slice, a start point, an end point, and a step. So for example, that slice above you could do as this tuple, from 0 to 10, stepping by 1. If it's a 1, you can actually just leave it off. That's the default. Okay? Is that clear? Because we're going to start passing these around. It's worth understanding what's going on there. Okay. So now, instead of passing entire objects, now that we've got the, we're gonna do shared memory. That'll be sort of some magic in this code. We're gonna slice out, instead of slicing up objects, or slicing out pieces of the array, we're just gonna talk about the slices that we would have taken out. So, this is the slice generator. It computes two steps, like how large should my pieces be, right there. It takes the array shape and just divides it by however many slices I want to do in each direction. And then loops over those the two sizes, and then just gives out a slice from a low point to some low point plus a step.
Does the slice imply what array it's operating on? The only arguments are the start and end, right?
Right, so it doesn't have to. It's detached from. Right, so I could do, if I have, some slice. Right? So 0, 1, and an implied 10. I can then do A of, and this is exactly equivalent to this. Do they take the same amount of memory? Well, you can't do this as an object. You mean, does this take up, this takes up 3 digits of memory. These are small as this. They're just, I'm a slice object, I have 3 values. When I do this, slice doesn't actually take up memory in the normal sense because it shares, remember, it shares memory with the original array. So when I do this, I'm still pointing underneath, it still points to the same block of memory that A originally pointed to. That's important to remember because if you modify something you've sliced, you've modified its parent. If you don't want to do that, you have to call copy or something like this. All right.
What is the yield?
Yield is, just makes it it's a Python generator. I'm not going to talk about this right now. I might do a lecture on them because they're really useful to know, but it's a Python specific thing. It basically turns this into, instead of having to return a list, so usually if I wanted to do this, I would build up a list, right, and give you the whole list. This is a way of shorthanding that and not computing it all at once. It's just like a list. I can iterate over it. I can do 4i in slices, or 4i in this function call, but it's a generator, which is just a sequence. I basically can ask for an object, and I can ask for the next object in this.
Same memory?
It does, especially if you've got if I'm going to be computing something that has a lot of I can have a generator that runs for a bazillion elements and give you 10 at a time, and not if you ask for the list of those, I run out of memory. If I just give you 1 at a time, it's fine. It's more just it makes much cleaner code, and once you learn them, you can find places to use them all the time. I hesitate to put it in there, but the code without it is uglier. It's worth reading about generators if you're going to be doing Python, or if you like Python. If you don't like Python, you probably don't care.
Using slice.
Yes.
Just a way of making everything. You could write the exact same code using just the implementation task.
Yeah, I could have just I guess I could have just given the array bounds, right? These are just cleaner objects to work with, right? It's right, because then I'm maybe talking at low and high and passing a bunch of stuff. This one I can just pass. Here's a piece, index with this, right? So it makes the low-level code. I needed you to see what's going on to understand that we're only going to serialize these slice pairs, and that's very small. So our serialization cost is going to drop. But the upper code is much nicer after we do this. All right, let me get to this example. So real quick, I'm going to get that slices. Think of it just as a list, but it's not technically a list. And I'm going to do this iteration over the slices instead. So I'm going to map over the slices instead of the original arrays. Okay? I've got some magic in here. If you want to read into it, you can. It's in the common.py function. But basically, I'm going to take those arrays and I'm going to make them shared. And then when I do this pool, all of the workers below see those values in the same memory space with basically no overhead. The operating system takes care of it. Okay? That's just magic. Are there questions about it? It's magic.
So the memory occupancy
Nope, nope. It maps to the same piece of physical RAM through just accounting tricks, basically. What's being serialized? Right, just the slices. Oop. Just the slices, which are small. So my serialization cost is dropped. All right, let's run this and then we'll hold the rest for later. So this one is in this. All right. So up from 488 to now, we got basically not quite a half a processor more using this approach by dropping the amount of serialization. Where's the overhead now? We're still passing a lot of messages around. And the rest we'll talk about later. You can read ahead if you want. It's in the repository for what happens next. But we're basically out of time, so let me just, again, well. So with block slices, we're now up to 550. Our target is still 800. That'll have to wait for another day, but that'll feed well into when we start actually doing threading. And so just a reminder, Friday, review. Any questions you have about anything? If you're confused about terms, concepts from previous lectures, this is a good time to ask them. Homework 1 questions, particularly things about RDD, loops, how to avoid them, what functions are out there, what do they do. Also a good time. Post on Piazza would be easiest for me to give a more complete answer, but feel free to come here and ask away during class time. So whatever. Have a good couple days. Don't drown.